The assessment of learning is perhaps the most challenging part of university teaching. I'm going to discuss some strategies for trying to create variable data for individual students. Why do we need variable assessment? Well, to be blunt, some students are naughty. To make it hard for the students to work together when they're not supposed to, we need to create variability in the questions that the students are answering. This won't guarantee that there's no illicit collusion, but it will reduce the likelihood of it by making it harder for students to work together. I've applied these strategies to both discrete maths, where it seems more suitable, and to calculus, where it's harder to implement. I've used three kinds of data to individualize assignments: randomly variable data, numerical data with individual parameters, and non-numerical data with individual parameters. By randomly variable data, I mean each student gets a certain set of data and there's no specific pattern as to how it happens. I used this in a group theory assignment where each student was given a different Cayley table. The students were required to identify the identity element, find the inverses of some elements, and so on. Each student received a 6-element Cayley table, which, unbeknownst to the students, were actually all isomorphic to each other. Well, the next question was how to get the Cayley tables to the students. And I suppose I could have driven around to their addresses, delivering them all to them, but instead I sent them as email attachments. So how did it work? Well, it took a long time. Then I hit on the idea of using a parameter instead. It seems natural to try a numerical parameter, and the obvious place to start was with the students' identity numbers. Now, if you interpret them as 7-digit decimal numbers, they're too big to be really useful, so you need to cut them down to size somehow. And the simplest way to do that is just to add up the digits. If the sum was prime, I asked the students to add 1 to it. Otherwise, they were to leave it as it was. This gave them their special number n. In the first example, they had to work out how many groups there were of order n, or do some research to find out the answer, how many abelian groups, what numbers might occur as the orders of the subgroups of a group of order n, and to describe all the symmetries of a regular n-gon. In the second example, if n was odd, they had to investigate the logical connective of alternative denial, while if it were even, they had to investigate joint denial instead. The fourth example was to do a bit of graph theory and to think about the complete graph Kn. Decide if it has a Hamilton circuit, a non-cyclic Hamilton path, an Euler cycle, or a non-cyclic Euler path. And then they had to use another number, p, which was the smallest prime divisor of n, and consider the complete bipartite graph Kpn. Does it have a Hamilton circuit, a non-cyclic Hamilton path, an Euler cycle, or a non-cyclic Euler path? And another graph theory example was given. A free tree with n vertices has how many leaves? What's the least and greatest number it could have? And a binary rooted tree with n vertices has how many levels? What's the least and greatest number of levels it can have? Well, a variation occurred when we had a list of 7 items and students had to pick one of those, but not to choose freely. They were to be assigned to the students. And the way to do that was to create a special index number. Add the digits in the ID number, divide by 7, write down the remainder, and add 1. Now, they had to start with this generator matrix for a group code and find a parity check matrix, H. Then they had to use the matrix H to produce the syndrome of their selected received word and make sure it matched the required syndrome in the list. A similar variation was given to the calculus students, where I wanted them to use a number which was to be 2, 3, or 4. They had to add up the digits in their ID number, divide the sum by 3, find the remainder, and add 2. Then they had to use this to answer a question about a circle and a question about a sphere, both having radius A. Now, the calculus students were less comfortable with this kind of question or this kind of task because they weren't familiar with the division algorithm, and some of them struggled with the idea of a remainder. The discrete math students didn't have that sort of difficulty. Now, there are some problems with the approach. One is that n, the special number, isn't always unique. And the other, of course, is that there's a lot more work in marking assignments that have variable data. Well, non-numerical data can sometimes be useful. And I use this for problems involving Huffman codes and language theory. We start with the student's name, but students' names are often too long, and I mean they vary a great deal in their style. So we decided to create a so-called special name using the first 6 letters of the official name. Then they had to insert that in a partially completed sentence to get something like, I am someone from RMIT, and use that sentence to construct a Huffman tree, then a Huffman code, and then to encode the sentence. They also had to use their special name to create an alphabet and use that alphabet to create palindromes of various lengths, or to work out how many palindromes of a specific length there might be. The problem with that is that the special name might not always be unique, and also some students had trouble constructing it. But also, some names made the task easier for some students than others, depending on how much repetition there was in the names. If there were few letters that were repeated, that made it harder. Well, you could change the special name so that it always had 6 distinct letters. So overall, what can I say about this experiment? It seems a good idea to use a parameter, and a numerical parameter is more versatile, but sometimes the non-numerical parameter can also be very useful, especially in some areas of discrete mathematics.